You know, I was looking at a construction site on my way in here today. They were pouring concrete, setting up steel beams, uh, really building the framework for something massive.
Right.
And it struck me that we usually talk about biology, especially biochemistry, in terms of, well, in terms of destruction.
Destruction. That's a bit of a grim way to start the morning.
Well, you know what I mean. We talk about burning calories. We talk about breaking down sugar for energy. We talk about the fight or flight response where we, dismantle our reserves just to survive the next 5 minutes.
Mm-hmm.
It's always about the hustle, the catabolism, the breaking down.
That is true. Catabolism, it really answers the question of survival. It's immediate, it's reactive, it's what happens when the alarm bells are ringing.
But today, we are flipping the script. We are looking at the opposite scenario. We are looking at what the body does when the alarm bells aren't ringing.
When the pantry is full.
Exactly. When the energy is abundant and the pressure is off, we're talking about construction.
We are talking about biosynthesis, specifically lipid biosynthesis. And if catabolism is, say, an act of desperation, biosynthesis is an act of confidence.
I love that framing. An act of confidence.
It really is. I mean, by building lipids, whether that's fatty acids for long-term storage or cholesterol for cellular structure, the body is making a profound physiological statement.
What's the statement?
It's saying we have enough energy right now, not just to survive the moment, but to invest in the future. We're going to take simple carbon units and weave them into these complex energy-dense structures to use days, weeks, or even months from now.
So this is the deep dive into how excess becomes structure. And before we get into the molecular nuts and bolts, we should set the ground rules.
For sure.
We are synthesizing insights from two absolute titans of the medical bookshelf today.
We are. We have Leninger Principles of Biochemistry and Harper's Illustrated Biochemistry.
And as always, I want to make this explicit to everyone listening. What we are doing here is an interpretation. We're creating a conceptual map. We are going to use metaphors and stories to help these pathways stick in your brain, but this is not a substitute for reading the texts.
Absolutely not. Think of this episode as your guide, or maybe your revision scaffold. Leninger is going to provide the architectural blueprint, the thermodynamics, the enzyme mechanisms, the beautiful logic of the chemistry.
And Harper?
Harper, on the other hand, is our chief medical officer. It grounds these principles in clinical reality pathology, disease states, and why this all matters when a patient walks into a clinic.
So keep those books handy. But for the next hour, we are going to walk through the factory floor of the human body. We're going to see how a simple 2-carbon unit is turned into the structures that define our cells.
And honestly, the why of this is just as important as the how. The body doesn't just let carbon pile up like trash, it actively manages it, it directs it. It's metabolic architecture.
Let's start with the geography then, because Leninger makes it very clear that in biochemistry, just like in real estate, location is everything.
It is. And this brings us to the first major design challenge the body faces when it decides to build fat, the separation problem.
Walk us through the layout here.
Okay, so we need to look at where our building blocks are. The fundamental unit for building fat is acetyl-CoA. Now, where do we mostly find acetyl-CoA?
It's in the mitochondria. That's where we break down pyruvate from carbohydrates. That's where we break down amino acids. The mitochondrial matrix is the engine room.
Exactly. The mitochondria is the incinerator. It's designed for oxidation, for burning things to generate ATP. But lipid biosynthesis, the construction of new fatty acids, happens in the cytosol.
The cytosol. So the main fluid filling the cell.
Right.
So we have the lumber in the basement, but the construction crew is up in the living room.
Precisely. And Leninger highlights a very specific biological logic for this separation. It's his principle number 2 when he discusses biosynthesis. We segregate these pathways to prevent a futile cycle.
A futile cycle. That sounds like my attempt to clean the garage.
In biochemical terms, it's even worse. If fatty acid synthesis and fatty acid oxidation happened in the same compartment, enzymes would be fighting over the same molecules. You'd spend expensive energy building a fatty acid, and an enzyme right next to it would immediately grab it and burn it back down.
Yeah.
You generate nothing but heat and waste a massive amount of ATP.
So the cell builds a wall, the inner mitochondrial membrane. It keeps the builders away from the burner.
Correct. But that creates a logistical nightmare. Acetyl-CoA, our primary building block, cannot cross that membrane. It does not have a transporter. It is physically trapped in the matrix.
So how do we get the materials to the job site? I mean, if the membrane is the border wall and acetyl-CoA doesn't have a visa, how does it get out?
It needs a smuggler. Or, to be more accurate, a shuttle. This is the citrate shuttle.
This is one of those mechanisms that seems so roundabout until you see the elegance of it.
It's a Trojan horse mechanism.
Yeah.
Inside the mitochondria, acetyl-CoA reacts with oxaloacetate. Now, oxaloacetate is part of the Krebs cycle. When they fuse, they form citrate.
Citrate, the stuff in lemon.
The very same. But here's the key. Citrate has a transporter. There is a specific protein, the tricarboxylate transporter, embedded in the membrane that allows citrate to slide right through and out into the cytosol.
So the acetyl-CoA hides inside the citrate molecule to sneak across the border.
Exactly. And once it's out in the cytosol, the disguise comes off. There is an enzyme waiting there called ATP citrate lyase. It cleaves the citrate back apart.
Into what?
It regenerates the oxaloacetate and, crucially, releases the acetyl-CoA.
So we've successfully teleported the building block, we disassembled the car, moved the parts through a small window, and reassembled it on the other side.
That's the mechanic of it, yes.
Okay.
But Harper adds a layer of nuance here that I think is critical for, the medical student or the clinician to understand. Citrate isn't just a passenger, it's a signal.
A signal.
Think about when citrate builds up. It happens when the Krebs cycle in the mitochondria is backed up. Why would the Krebs cycle be backed up?
Because the cell has plenty of energy. If ATP is high, the engine idles. It doesn't need to spin the turbine.
Exactly. High ATP inhibits the Krebs cycle enzymes like acetylcitrate dehydrogenase. So acetyl-CoA and citrate start piling up.
I see.
So when citrate floods out into the cytosol, it is chemically shouting a message, "We are swimming in energy down here. The engine is full. Stop burning and start building."
That is elegant. The very presence of the building material acts as the work order to start construction.
It's a perfect integration of supply and demand. But, as any contractor will tell you, having the materials is only half the battle. You also need the budget to pay for the work.
And in biochemistry, budget usually means electrons.
It does. But we have to be specific. In the mitochondria, when we burn fuel, we use NAD+ to pick up electrons. That's for generating currency, ATP.
Right.
But biosynthesis requires investing electrons. We need reducing power. We are taking a molecule that is already oxidized, and we are forcing electrons back onto it to build high-energy bonds.
And for this, we use NADPH.
Yes. NADPH. The P stands for phosphate, structurally. But for our listeners, I would suggest thinking of the P as standing for purchasing power. NADH is for the bank.
Yeah.
NADPH is cash in hand for construction.
Leninger makes a big point of this chemical segregation. Catabolism uses NAD+. Anabolism uses NADPH. It's a fundamental design principle.
It is.
So where does the cell get all this cash? We're in the cytosol now. Where is the NADPH coming from?
Harper and Leninger identify two main generators. The first, and maybe the most famous, is the pentose phosphate pathway.
Ah, the PPP.
Exactly. In tissues like the liver and mammary glands, which are basically professional fat factories, this pathway is running at full tilt, just churning out NADPH.
And the second source?
The second source is actually a beautiful example of recycling connected to our shuttle. Remember, we split citrate into acetyl-CoA and oxaloacetate in the cytosol.
Right. The oxaloacetate is now stuck out there.
And the cell needs that oxaloacetate back in the mitochondria to keep the Krebs cycle running. But oxaloacetate can't cross the membrane either.
It seems like nothing can cross this membrane.
It's a very strict border. So the cell converts oxaloacetate to malate. Malate can cross, sometimes, but often it takes a different route. An enzyme called malic enzyme converts malate to pyruvate.
Okay.
And in that specific reaction, as it chops off a carbon, it generates NADPH.
So the shuttle system itself helps pay for the construction costs.
Exactly. By returning the shuttle vehicle in the form of pyruvate, we generate the fuel, the NADPH, needed to build the cargo. It's a self-reinforcing loop.
Okay, let's take a breath and check our position. We are in the cytosol. We have successfully transported our acetyl-CoA, which are the bricks. We have generated our NADPH, the mortar, and the money. Now we need to actually start building.
And this brings us to section 2 of our outline, the commitment. In every metabolic pathway, there is a point of no return, a step where the cell says, okay, we are doing this.
For lipid synthesis, that step is the creation of malonyl-CoA.
Correct.
Yeah.
Up until now, that acetyl-CoA in the cytosol could theoretically be used for other things. But once we turn it into malonyl-CoA, we are building fat. There is no other path.
And the enzyme responsible for this big decision is acetyl-CoA carboxylase, or ACC. Leninger treats this enzyme with a lot of reverence. It seems to be the central control tower.
It is the gatekeeper, and physically, it's a fascinating machine. ACC uses a helper molecule called biotin, vitamin B7.
I see biotin in hair and nail supplements all the time.
That's the one. In this context, biotin acts as a prosthetic group attached to the enzyme. Leninger described it almost like a long, flexible, robotic arm.
Okay.
The enzyme uses ATP to grab a molecule of CO2 bicarbonate, really, and attach it to the tip of this biotin arm.
Like loading a payload onto a train.
Exactly. Then this arm swings over, it physically moves across the enzyme surface, and smacks that CO2 onto the acetyl-CoA molecule.
So we go from a 2-carbon acetyl-CoA to a 3-carbon malonyl-CoA. Boy, I remember looking at the pathway later on, and we eventually release that CO2 again.
We do.
Why go through the trouble and spend the ATP to glue a carbon on just to rip it off later?
That is the million-dollar thermodynamic question. And the answer is leverage. Attaching that CO2 is like compressing a heavy spring. It activates the molecule.
Okay.
Biosynthesis is an uphill battle against entropy. By adding the CO2, we are storing potential energy. Later, when we want to link carbons together, we pop that CO2 off, and the energy released from that spring drives the formation of the new chemical bond.
Ah, I see. It's a thermodynamic investment. It makes an otherwise difficult reaction happen.
The CO2 is the push. But because this step burns ATP, and because it commits the cell to a very expensive process, ACC is regulated tighter than Fort Knox. Harper describes a dual control system that is just. It's the police force of metabolism.
Let's break that down. We have immediate control and we have long-term control.
Right. The immediate control is allosteric. It happens in seconds, and it involves our old friend citrate.
The signal from the mitochondria again? It's everywhere.
It's the master signal. When citrate concentrations rise in the cytosol, citrate physically binds to the ACC enzyme. And Harper describes this amazing physical transformation.
Wow.
The inactive ACC enzymes are these separate little unistimers. But when citrate binds, they polymerize. They link up into these long, active filaments.
So the enzyme literally assembles itself into a working production line when the signal arrives.
It does. It changes shape and switches on. Its molecular weight increases into the millions. But if the product starts piling up, if you have too much palmitoyl-CoA, the finished fat, floating around, it does the opposite.
Product inhibition.
Yes, it acts as a wedge. It breaks the filaments apart back into inactive dimers.
Feedback inhibition. Stop making cars. The parking lot is full.
Precisely. But then you have the hormonal layer. This is the State of the Union address. This comes from insulin and glucagon epinephrine.
This connects it to what we eat and our stress levels.
Directly. When you eat a big meal, blood sugar spikes and insulin rises. Insulin is the build-and-store hormone. It activates a phosphatase enzyme that strips a phosphate group off the ACC.
And that does what?
In the language of this specific enzyme, dephosphorylation means go. It activates the enzyme.
But if I'm starving, or if I'm running from a tiger,
then glucagon, or epinephrine, hits the cell receptor. They trigger the phosphorylation of the enzyme. This is mediated by a kinase called AMPK, AMP-activated protein kinase.
And phosphorylation is the stop signal.
Yes, it turns ACC off, which makes perfect sense, right? If I'm running for my life, I shouldn't be spending precious ATP to build fat reserves. I need to burn everything I have.
It's an immediate cease and desist order to the factory.
Exactly. But there is one more piece of regulation here that is just so clever. It's the crosstalk between synthesis and burning.
Oh, right. We mentioned earlier that the membranes separate the two factories, but there's an extra lock, isn't there?
I think this is one of my favorite details in systems biology. Think about it. When ACC is active, you are churning out malonyl-CoA in the cytosol. Its concentration rises.
Okay.
That malonyl-CoA doesn't just sit there waiting to be used. It actively binds to an enzyme on the mitochondrial surface called carnitine acyltransferase I, or CET.
And KI is the bouncer.
CTI is the bouncer that lets fatty acids into the mitochondria to be burned. It's the gatekeeper for beta oxidation.
So high malonyl-CoA, which means we are building fat, locks the door to the incinerator.
Yes. It physically prevents fatty acids from entering the mitochondria. It ensures that you cannot simultaneously synthesize fat and burn fat. It's a fail-safe to prevent that futile cycle we talked about at the start.
So the very first brick of the new wall you're building, the malonyl-CoA acts as a doorstop to keep the demolition crew out.
That is a wonderful analogy. It shows how integrated the logic is. You don't need a central brain to coordinate this second by second. The molecules do the thinking for you.
Okay, we've committed, we've made malonyl-CoA, the bouncer has locked the incinerator door. Now we need to actually assemble the chain. We need the machine.
Enter the fatty acid synthase complex, FASI.
Leninger describes this thing like a Swiss Army knife. It's massive.
It really is. In bacteria, fatty acid synthesis is done by a bunch of separate little enzymes floating around. But in vertebrates, in us, evolution has welded them all together. FASI is a single, massive polypeptide chain.
One chain.
One chain. But it folds into a structure that has 7 different active sites.
7 tools in one handle.
Right. And it works as the homodimer, meaning 2 of these massive chains work side by side.
Yeah.
But the coolest part is the tether.
The acyl carrier protein, the ACP.
Yes. The ACP has a prosthetic group 4 phosphopantothene. It's a long, flexible arm.
Another arm. We had the biotin arm earlier.
Biochemistry loves a flexible arm. It's the best way to move things around on the nanoscale. Think of FAS like a robotic assembly line.
Yeah.
But instead of the car moving down a conveyor belt to different stations,
Right.
the car is bolted to a robotic arm, the ACP, that swings it around to different welding stations, the active sites, all within the same enzyme complex.
That is a great visual. So the substrate never leaves the enzyme. It just gets passed from tool to tool.
Exactly. This is called substrate channeling. It's incredibly fast and efficient because you don't have to wait for the molecule to diffuse to the next enzyme. It's already there.
So walk us through the cycle. We are building palmitate, which is the standard issue, 16 carbon saturated fat. How does the FAS complex actually do
It's
it?
a repeating 4-step dance. Leninger details this beautifully. The steps are condensation, reduction, dehydration, reduction, CRDR.
Let's take them one by one. Step 1, condensation.
Okay, so the enzyme takes an acetyl group, which is 2 carbons, and a malonyl group, 3 carbons. It condenses them together. In the process, that CO2 we added earlier with so much effort, it pops off.
That's the spring releasing.
Boom. The CO2 leaves, driving the reaction forward. We fuse the remaining carbons to get a 4-carbon chain. But here's the catch. Chemically, it's ugly. It has a ketone group, a double-bonded oxygen sticking off the side.
Right, and we want a hydrocarbon chain. Just carbons and hydrogens. We need to get rid of that oxygen.
That leads to step 2, reduction. We bring in our cash, the NADPH. It donates electrons and a hydrogen to turn that carbonyl, the C double bond O, into a hydroxyl, a COH, an alcohol.
Okay, so now it's an alcohol, still has an oxygen. So step 3, dehydration.
Just like it sounds. We remove a water molecule, H2O, that takes the oxygen away completely. But it leaves a scar to double bond between the carbons.
And step 4, reduction again.
We need to smooth out that scar. We want a saturated, flexible, single bond. So NADPH comes in again, donates more electrons and hydrogens, and flattens that double bond into a single bond.
So we went from a clunky chemical structure with oxygen hanging off it to a sleek, saturated hydrocarbon tail.
Exactly. And now we have a 4-carbon chain tethered to the enzyme's robotic arm. The ACP swings it back to the start position, grabs another malonyl-CoA, and repeats the cycle.
CRDR.
CRDR. Each cycle adds 2 carbons.
And it keeps going until... Does it just make an infinitely long string?
No. And this is amazing. The enzyme has a built-in ruler. The pocket where the chain grows is exactly the size of a 16-carbon chain. Once the chain hits 16 carbons, palmitate, it physically doesn't fit in the elongation site anymore.
It gets jammed.
In a way, it effectively pushes into the active site of the final enzyme activity, thioesterase. Thioesterase acts like a pair of scissors. It snips the tether, and the finished palmitate floats away.
That's incredible. It prints a standardized 16-carbon part and then automatically ejects it.
And it is expensive. Leninger does the math for us. To make one single molecule of palmitate, it costs 8 acetyl-CoA, 7 ATP, and 14 NADPH.
14 NADPH. That is a massive investment of reducing power.
It is. That's why fat is so energy dense. You are packing all that potential energy into those bonds. It's a savings bond with a very high maturity value.
So now we have palmitate. It's the standard model. But looking at Harper, the body needs a lot more variety than just 16 carbon-saturated fats.
That's right.
We need longer chains for the brain. We need unsaturated fats with double bonds for membranes. How do we customize this basic part?
The FAS complex in the cytosol is a one-trick pony. It only makes palmitate. For anything else, we have to go to the accessory shops, specifically the smooth endoplasmic reticulum, or ER.
This is where we do elongation and desaturation.
Right. Elongation is pretty straightforward. It uses a similar mechanism to FAS, adding carbons 2 at a time using malonyl-CoA, but it happens with separate enzymes embedded in the ER membrane. This is how we get stearate, which is 18 carbons, or the very long chains needed for myelin in the nervous system.
But desaturation adding double bonds, that's trickier. And Harpo points out a really critical biological limit here.
Yes, the delta-9 limit. It sounds like a sci-fi boundary, but it dictates human nutrition.
What is it?
Mammals have an enzyme called delta-9 desaturase. It can put a double bond between the 9th and 10th carbon. This allows us to turn stearate, which is an 18-carbon saturated fat, into oleate, which has 1 double bond.
Oleate, the main fat in olive oil.
That's the one. We can make that.
But we can't go past carbon 9.
No. We lack the enzymes to introduce double bonds at the delta 12 or delta 15 positions. This is a fundamental evolutionary gap in vertebrates.
And this explains why we have essential fatty acids.
Exactly. Plants do have these enzymes. Plants can make linoleate, which is an omega-6, and alpha-linolenic acid, an omega-3. We physically cannot manufacture these structures. We must eat them.
I think most people hear essential fatty acids and just think, eat your walnuts or take your fish oil. But why are they essential? Why does the body care so much about having a double bond at position 12 or 15?
It's not just for burning. Harper emphasizes that these essential fats are precursors. They are the raw material for a class of molecules called eicosanoids.
The eicosanoids, these are the localized signaling molecules, right?
They're incredibly potent short-range hormones. We take arachidonic acid, which we make from the dietary linoleate, and modify it to create prostaglandins, thromboxans, and leukotrienes.
These control things like inflammation.
Everything. Pain, fever, the sleep-wake cycle, blood clotting, the constriction of airways during an asthma attack. This is where biochemistry meets the pharmacy aisle.
Right. Harper explicitly mentions NSAIDs here, aspirin and ibuprofen.
They work by inhibiting the enzyme cyclooxygenase, or COX. The COX enzyme is what turns arachidonic acid into prostaglandins. So you take an aspirin for a headache, you are literally jamming the gears of a lipid modification pathway.
You are stopping the production of the lipid signal that says, ouch.
That's precisely it.
It's wild to think that a headache pill works by interfering with lipid biochemistry. We usually think of fats as passive, just storage tanks.
That's the biggest misconception. Lipids are active players. They are signals. They are structural. They are everything.
Speaking of storage tanks, though, we do have to talk about storage. We've made these fatty acids, but we can't just have them floating around loose. They're detergents. They dissolve our cell membranes.
Correct. Free fatty acids are toxic. We have to neutralize them. We do that by esterifying them to glycerol to make triacylglycerols or tags.
The safe storage form.
Yes. 3 fatty acid tails clipped onto a glycerol backbone.
And Leninger brings up insulin again here, naturally.
Insulin's the master builder. It doesn't just turn on the synthesis of fatty acids via ACC, it also promotes the synthesis of tags. And Leninger contrasts this with diabetes.
The starvation in the midst of plenty scenario.
Exactly. In uncontrolled type 1 diabetes, you have high blood sugar, but no insulin signal. So the body thinks it's starving. It fails to store the sugar as fat. Instead, it aggressively breaks down its fat reserves.
Which explains the weight loss.
It explains the rapid weight loss despite being hungry and having sky-high blood sugar. The metabolic logic is completely broken.
There's also a mention of something called the futile cycle of tags. The body seems to constantly build and break down tags between the liver and adipose tissue. Why would it do that? It sounds wasteful.
It's the triacylglycerol cycle. About 75% of the fatty acids released from fat cells are actually just sucked back up and restored. It uses a lot of energy. But biochemists believe this is about readiness.
Readiness.
If you keep the machinery greased and running, constantly mobilizing and restoring, you can respond much faster if suddenly you do need to mobilize energy for a crisis.
Oh, I see.
It's like keeping a car engine idling at a stoplight rather than turning it off completely. You burn gas, but you can move instantly when the light turns green.
That is a fascinating trade-off, efficiency versus agility.
And biology often chooses agility.
Okay, so that's the world of fatty acids, fuel, insulation, and signals. Now we need to pivot to the other titan of lipid biochemistry, cholesterol.
Cholesterol, a molecule with bad reputation, but an absolutely essential function.
It looks totally different from fatty acids, doesn't it?
Completely. Fatty acids are long, flexible chains. Cholesterol is a rigid 4-ring steroid structure. It's like a molecular plate.
And we don't burn it for energy?
Never. You cannot burn cholesterol for energy. It has 0 caloric value to the human body in terms of ATP generation.
So why do we make it?
Architecture. It slots into cell membranes to control their fluidity. It keeps them from getting too floppy in the heat or too brittle in the cold. It's the structural integrity of the cell.
And it's a precursor.
Right. It's the precursor for all our steroid hormones, testosterone, estrogen, cortisol, and for bile acids, which help us digest fat.
Harper and Leninger outline the synthesis. And wow, is it complicated. 27 carbons.
It is a monumental biosynthetic achievement. It involves nearly 30 enzymes. It starts with acetyl-CoA, just like fatty acids, but the path diverges very early on.
The first stage is the setup. We condense 3 acetyl-CoAs together to make something called HMG-CoA.
And here we hit the celebrity enzyme of this pathway, HMG-CoA reductase.
This is the committed step.
It is. This enzyme converts HMG-CoA into mevalonate. Once you make mevalonate, you are committed to making sterols.
Right.
There's no going back.
And because it's the bottleneck, it's the target, Harper explicitly links this to statins.
Yes, drugs like simvastatin or atorvastatin, they are competitive inhibitors of HMG-CoA reductase. They mimic the transition state of the reaction.
So they act like a fake key getting stuck in the lock.
Exactly. They bind to the enzyme with extremely high affinity, thousands of times stronger than the natural substrate. They effectively jam the machine. If you block this one enzyme, you throttle the body's internal production of cholesterol.
But the body fights back, doesn't it? The regulation here is incredibly sophisticated. Leninger goes into deep detail about something called SREBP.
The sterol regulatory element binding proteins. This is, in my opinion, one of the most elegant feedback loops in all of biology. It plays out like a spy movie.
Set the scene for us.
Okay. Imagine SREBP is a dormant messenger. It lives in the membrane of the endoplasmic reticulum, the ER. It's anchored there by another protein called INSIG. And INSIG is a sensor.
What is it sensing?
Cholesterol levels in the membrane. As long as there's plenty of cholesterol in the membrane, INSIG holds on to SREBP tight. It says, stay here, we have enough.
But if cholesterol levels drop?
If the membrane gets depleted of cholesterol, INSIG changes shape and lets go. SREBP is now free, but it doesn't go to the nucleus yet. It travels in a vesicle from the ER to the Golgi apparatus.
Moving to a different organelle.
Right. In the Golgi, two specific proteases enzymes that cut proteins are waiting. They act like scissors. They snip off the active domain of the SREBP protein.
So they release the messenger.
Yes. That snipped off fragment is the transcription factor. It travels into the nucleus, binds to specific DNA sequences, and turns on the genes.
And what genes does it turn on?
All the genes needed to get more cholesterol. It turns on the gene for HMG-CoA reductase to build more, and the gene for the LDL receptor to steal more from the blood.
It's a demand-driven supply chain.
Exactly. And if cholesterol gets too high, the SREBP stays trapped in the ER. No gene expression. And Leninger notes a brutal efficiency here. High cholesterol also triggers the destruction of the existing HMG-CoA reductase enzyme.
What? Really?
Oh, yeah. The cell ubiquitinates it, basically tagging it for the trash compactor.
So it stops building new machines and destroys the old ones?
Ruthless. It ensures that you never waste energy building cholesterol you don't need.
Let's quickly touch on the construction itself. We go from mevalonate to activated isoprenes.
These are like molecular Lego bricks. 5 carbon units, we stick them together to make squalene.
Squalene, that's a 30-carbon chain.
Right, it's a long, squiggly chain. Then, in a remarkable origami move, an enzyme called cyclase grabs it and folds it instantly into those 4 fused rings. It becomes alosterol.
And from lanosterol, it gets polished and refined, losing 3 carbons to finally become cholesterol with its 27 carbons.
A lot of energy, a lot of enzymes, all to create this rigid little plate that keeps our membranes working.
So we've built the fats, we've built the cholesterol, now we have to integrate this into the whole body. Leninger talks about the Land cycle. What is that?
The Land cycle is about renovation. We tend to think of cell membranes as static, like a brick wall, but they're constantly changing.
Renovation.
Yes. Phospholipids in the membrane get damaged by oxidation, or maybe the cell decides it needs to change its fluidity. The Land cycle allows enzymes to snip off one fatty acid tail from a phospholipid and replace it with a different one.
So if I start eating a lot of fish oil, lots of omega-3s, this is how they get into my cell membranes.
Exactly. The cell remodels its surface to reflect your diet. It pulls out an omega-6 and slots in an omega-3. This changes the physical properties of the membrane in the signaling environment.
And then there's transport. Harper gives us the overview of lipoproteins. Because oil and water don't mix, we can't just dump cholesterol into the blood.
No, it would form a sludge. We wrap it in protein and phospholipid spheres. We have LDL, low-density lipoprotein, which delivers cholesterol from the liver to the tissues.
The bad cholesterol.
Colloquially, yes. Because if you have too much, it dumps cholesterol or you don't want it, like in your artery walls. You have HDL, high-density lipoprotein.
Good cholesterol.
Right. It does reverse cholesterol transport. It goes out, picks up excess cholesterol from the tissues, and brings it back to the liver for disposal.
Disposal meaning bile.
Mostly bile. This is the only way to really get cholesterol out of the body. You turn it into bile salts, store it in the gallbladder, and secrete it into the gut.
Which brings us to the diseases Harper warns us about.
Atherosclerosis is the big one. Leninger describes the pathology in detail. It starts with oxidized LDL getting stuck in the arterial wall. Macrophages, our immune cells, come to eat it. They are trying to clean up the mess.
But they eat too much.
They engorge themselves on the lipids. Under a microscope, they look foamy. because they are packed with fat droplets. We call them foam cells. Eventually they die.
And when they die?
They release all that fat in a storm of inflammatory signals. It forms a plaque. It's basically a necrotic scab inside your artery made of fat and dead immune cells.
That is a gruesome image. And gallstones.
Gallstones are often just precipitated cholesterol. If the bile has too much cholesterol and not enough bile salts to dissolve it, it crystallizes. It's like putting too much sugar in iced tea. Eventually, it falls to the bottom.
And finally, obesity and type 2 diabetes. This connects back to our intro.
It does. The system we described, ACC, fatty acid synthase, insulin regulation, evolved in a world of scarcity. It is designed to be incredibly good at capturing excess energy and storing it. It assumes that winter is coming.
But in the modern world, winter never comes.
Exactly. We are in a state of permanent feast. The machinery is working too well. We store and store and store. Eventually, the storage tissues, the adipose tissue, are full. Fat starts spilling over into the liver, into the muscles.
And this causes lipotoxicity.
Yes, the regulatory signals break down because the system is overwhelmed by abundance.
So let's bring this all home. We've covered the shift from burning to building. We've mapped the factory floor from the citrate shuttle to the FAS robot arm. We've seen the rigorous control of ACC and HMG-CoA reductase.
It really is an architectural masterpiece.
What's the big takeaway for you when you look at all these pathways together?
For me, it's the concept of biological economics. Every step we discuss, the use of NADPH, the ATP required for biotin, the regulation by citrate, is about cost-benefit analysis. The body treats energy as a precious resource. It doesn't build unless it can afford to, and it protects its investments with sophisticated locks.
It's a system designed for efficiency.
Ruthless efficiency.
Here's a provocative thought to leave you with. We spent this hour admiring the elegance of these enzymes. ACC, FAS, HMG-CoA reductase, they are miracles of evolution. But are they now our enemy?
That is the paradox. We have a thrifty genotype. The very enzymes that saved our ancestors from starvation during the Ice Age are the same enzymes driving the metabolic syndrome epidemic today.
Our biochemistry hasn't changed.
Our biochemistry hasn't changed, but our environment has flipped. We are running 10,000-year-old software in a modern hardware world.
And that efficiency is now a liability.
It is. So next time you sit down to a high-carb meal, maybe a big bowl of pasta, visualize that citrate shuttle. Visualize the citrate pouring out of your mitochondria, signaling the ACC to polymerize to filaments, and starting up the 3D printers to turn that pasta into palmitate.
It's not just digestion, it's construction.
And your body is betting that you're going to need that energy later, even if you probably won't.
Thanks for diving deep with us today.
It was a pleasure.